for coming. Yeah, so in my talk, I'll talk about also the inverse rendering problem, but from a more physics-based perspective. So this is an outline of my talk. First, I'll do a quick introduction to motivate the problem. And then I'll first talk a bit about physics-based differentiable rendering, which is a key ingredient to enable solving the inverse problems. And then I'll talk about various aspects in inverse rendering. And finally, I'll discuss some of the future directions and the remaining open problems. So yeah, let's get started. So before talking about inverse rendering, I'll briefly talk about, well, the forward rendering problem, which is a very mature topic. It has been studied in computer graphics for a long time. So the forward rendering problem takes some scene parameters, some 3D assets, and then produces, well, an image. When we talk about physics-based forward rendering, we mean the rendered image has to properly simulate certain light transport effects so that it mimics what a visual camera would have seen. So the power of physics-based rendering lies in the ability to capture complex light transport effects, sometimes also referred to as global illumination effects, such as soft shadows, interreflection, and some volumetric or subsurface scattering effects. So on the bottom, we show a rendered image with material property captured from real materials. So you can see that they can really mimic what these materials appear in the real world. Of course, today we are not focused too much on the forward problem, but rather we are interested in the inverse problem, meaning that instead of going from scene parameters to images, we are interested in solving the inverse problem where we take one or multiple images or photographs, and in turn, we want to infer the one or multiple scene parameters, right, including the shape of an object, the reflectance of an object, the illumination condition, and so on. So hopefully you have already seen many discussions about the applications of this problem. The applications can range from computer vision and imaging problems to AR and VR and even robotics applications. So of course, today our workshop is mainly about creating digital twins, and that's also a important application of inverse rendering. For example, taking a set of input images, one can jointly optimize the shape, reflectance of an object, as well as the illumination conditions. With such information, we basically obtain a digital twin of some real-world objects, and then we can put them, basically these are basically digital assets, which can be then integrated into novel environments and achieve relighting and even simulations. I'll briefly talk about this work in more details later, but this is a clip of the Meta Connect keynote in 2022. So you can see these are some objects, basically digital twins, created using physics-based inverse rendering. So you can see if we take them, you can see, well, it's reliable. You can see the reflection on the surface of the leaves, and because they also have like well-defined surfaces and everything, they can be easily relit. You can even like, throw them. You can see them rolling around, all thanks to the complete asset created from this process. Okay, so typically, inverse rendering problems are formulated as an optimization where we take a set of target images or photographs. We want to seek for the scene parameters so that some loss, normally some sort of image loss, defined between the target images and the rendered images are minimized. And of course, to solve these problems, one can use stochastic gradient descent, right, by initializing with some basically guess of the scene parameters, we can iteratively update the parameters until a convergence is reached. And of course, to actually estimate the gradient of the loss with respect to the sinc parameters, one can apply the chain rule, which in turn requires differentiating basically the rendering function. Right? That's where differentiable rendering is needed. Now be aware that although my talk will focus on like the physics-based pipeline of this, it applies also to many other non-physics-based pipelines, such as a nerve pipeline or Gaussian splat pipeline. It's pretty much the same. It's just the rendering function is defined differently, right? So, but again, in my talk today, I'll focus on the type of rendering functions that are physics-based. Although, again, this pipeline applies also to nerve and Gaussian splatting scenarios. And of course, this is also known as analysis by synthesis. It's nothing new by itself. Okay. Okay, so that's just a really high-level overview. But before talking about the inverse pipeline and other aspects, I will briefly talk about what's in the orange box, which is the differentiable rendering part, which is, well, in this case, physics-based differentiable rendering. So what is differentiable rendering? Hopefully most of you are already familiar with this aspect in general, because again, it applies also to non-physics-based scenario, right? If you render nerve or Gaussian splat, it has to be differentiable as well. So in general, differentiable rendering is about computing derivative images with respect to certain parameters. It can be position of an object, opacity of a Gaussian, depending on the scenario, right? So in this case, I'm showing an example. On the left is it's a forward rendering of a dining room. The dining room is lit by sunlight outside, right? On the right-hand side, I'm visualizing the derivative of this image with respect to the location of the sun, right? If the sun moves a bit, what's going to be the change rate, right, of all the pixels? So this is the problem that differentiable rendering aims to solve. Unfortunately, at least when it's applied to physics-based rendering, is a non-trivial problem. One reason is because the relation between rendered images and the scene parameters can be very complex. Again, it's not always complex, depending on your underlying rendering model. But when it comes to physics-based rendering, this relation can be complex. So let me use this image as an example again. So if we ask the question, how would this image change with respect to the optical density of this blue line, which is also called croissant, as shown in the blue box? If you look at this closely, this is really not even a local problem, because if you change the optical property of this blue line, it affects elsewhere in the image, right? Because of reflection of this blue line on the other glass and so on. So this is really kind of a global effect to some extent. So that makes the problem harder. Another difficulty, which I think these days more and more people are aware of this, but I still want to emphasize it, is that getting correct derivatives is more than applying autodiff. For example, let me give this toy problem, where if you look at this integral, where the integrand is basically a step function, right? Which is this, when x is less than p, it returns 1, and otherwise it returns 1/2. And we are trying to differentiate with respect to p. However, because p is in a kind of control flow, right? P is not in any statement per se. If you apply autodiff, what happens if you apply autodiff to the two return statements, 1 versus 1/2, and you get 0 100% of the time. So if you just do this, automatic differentiation will tell you the derivative is going to be 0 always. And apparently this is not correct, right? The true derivative is not 0. So it's incorrect. So that's another reason why this can be challenging. So yeah, so I'll explain what the proper way to handle this is very briefly. The reason I just discussed integrals is because rendering largely amounts to estimated integrals, right? Even if you only consider direct illumination, you still need to integrate over all incoming directions, right? When you have environmental lighting and so on. And in our case, when you want to talk about general physics-based forward rendering, a well-known formulation introduced by Eric Veitch in 1997 is called the path integral formulation. Without going into all the details, this formulation tells us that the color of a pixel, or the radiance value coming out of a surface point, equals an integral, a high-dimensional integral, over all light passes connecting a light source and the pixel, right, that's seen by a camera. And the contribution of the light path is captured by this measurement contribution function, which again, I'm omitting most of the details. However, something I want to emphasize here is that this function is normally discontinuous. So think about the step function toy example I just illustrated. The reason why it's discontinuous, well, it's because of visibility. So if you look at this example, the toy Cornell box scene, there are multiple edges. For example, if you look at the area light on the ceiling, right, it's an open surface, it's a square, right? So the edge of the square creates discontinuities. And also, if you look at the cube or the edge of the box, there are normal discontinuities, right? If you look at the cube, the surface normal have a sudden change along the edge of the cube. So that's a certain type of discontinuity. And of course, the third type of discontinuity are silhouettes, right? That's the visibility-related discontinuities. Something to be aware is that the third type of discontinuity generally exists regardless how smooth your surfaces are, as long as you have occlusions, right? So that's kind of problematic. So let's go back to our toy example I showed earlier. If we want to differentiate this toy integral, the correct way to do it is actually to break this integral into two, right? Because we're integrating for the first one, we integrate from 0 to p, and the other one from p to 1. We basically break this step function into two constants, right? It's because it's a piecewise constant function, so we can break into two. So by properly calculating this derivative, we know that, well, certainly the derivative is not 0 in this toy case, it's actually 1/2. Fortunately, this idea can be generalized to higher dimensions. For example, when applied to 2D integrals, there's a famous theorem called Raynaud's transport theorem, introduced actually to continuum mechanics more than 100 years ago. It states that, in general, the derivative of 2D integral equals an interior term, which is actually obtainable via automatic differentiation, because all you need is to differentiate the integrand. However, there's this boundary term that you have to introduce that captures all the discontinuities. Okay, so again, these are all well-known things, and some of the earlier works in graphics have adopted this relation for physics-based rendering. So something we did earlier, which also resulted in an outstanding PhD thesis award at SIGGRAPH, is to generalize that idea to path integrals. So it basically, again, it's a very technical thing, so I'm just going to give a very high-level overview of how it looks like. It basically states that if we differentiate a forward rendering path integral, again, these are high-dimensional integral over all passes connecting a light source and a camera. It also contains the derivative also involves an interior term and a boundary term, where the interior term is again kind of obtainable using autodiff. You just take the forward algorithm, you autodiff the integrand to kind of get the interior term. However, there's a boundary term which is unique to differentiable rendering here, and mathematically this boundary term is defined over all passes connecting a so-called boundary segment, which is a segment that lies on a silhouette, right? Because that's where the discontinuities are. So again, how to numerically estimate this is not trivial, but I'll omit some of those details for today, because our main focus will be the inverse problem. So to be able to show demonstrate a little bit about the capability of this type of framework. I'm showing a simple synthetic example here. So in this example, we have an apple embedded in a glass cube. You are seeing multiple of the apple because of all the reflection and refraction effects. There's only one apple here, okay? So in this two-way problem, we jointly optimize the position of the apple and the surface roughness of the glass. Okay, you can imagine this really requires properly simulating the light transport effects. And with proper gradients, that's really not a problem. And again, I'll show more real-world examples later. And later, we generalize this framework to also support volumetric light transport. As a result, we can do optimizations like this. So on the top, we optimize the position of a light source. You can see in this example, we have a synthetic scene filled with participating media, so you can see all the volumetric caustics and everything. So we can do optimization like this. On the bottom, where we optimize the shape of the bunny and also the surface roughness and also optical density. So that can be done too. So again, all these are very, very toy problems, and but they kind of demonstrate the power of these underlying methods. Okay. So next, I'll start talking about the actual main focus, the actual inverse rendering problem and the pipelines. So this is, again, this is a slide I showed earlier, and it demonstrates the analysis by synthesis pipeline. Again, it's nothing new by itself. However, when we have the differentiable rendering methods that I just briefly discussed, we can do some interesting things using this well-established pipeline. So in 2021, this is kind of the first paper that we tried to embed physics-based differentiable rendering into these inverse pipelines. So in this work, we basically took a number of multi-view photos and jointly optimized, say, the shape and the material properties of an object. So these are some of the results. I think they are already kind of high quality. At that point, some issues are that it requires a bunch of remeshing, which can be a pain because it's just a mesh-based representation. And also, the speed of the system at that point is not very great, was not very great. So the whole pipeline could take a very long time. But this was one of the early works that first incorporated physics-based differentiable rendering into this inverse pipeline. Then this is more recent work. I think you might have seen this discussion about this work in a few talks already. This is a new PBIR method, which is also the one I briefly talked about at the beginning of my talk. So this is a work that also uses physics-based differentiable rendering to jointly optimize the shape and the material and the illumination condition for one object, not at scene level yet. So briefly speaking, the reason why it's called neural PBIR because it really combines neural methods as well as physics-based pipelines, which I think is a very reasonable thing to do. So you can see shown on the bottom, starting with, I can highlight this. Starting with a news-like pipeline, we obtain an initial estimation of the object geometry. Then we have this basically distillation step that obtains a brief estimation of light as well as material properties at each vertex of the mesh. And then the green box uses basically the physics-based pipeline to refine the distilled material and lighting and all the information and apply basically a joint optimization that drastically improve the final quality of the model, which is again why we call it neural and PBIR, because the pipeline uses both neural methods and physics-based ones. So this is a very robust method. And so you can see compared with some of the earlier methods, this pipeline achieves considerably better quality, as demonstrated here. And of course, later we applied our method to the Stanford ORB dataset. Again, compared with the previous methods that do go beyond view synthesis, our method produces considerably higher quality in terms of reconstruction. Okay. So we actually have done a bit more beyond new PBIR. So this is a work that we presented at SIGGRAPH Asia in 2023. So in this work, what we did is we take a single image. It's a semi-automatic pipeline. It's not fully automated yet. And the goal is to, well, it's a basic asset creation. The goal is to create taking a single image of a room. The goal is to create a 3D scene of that room. As you can see, it's not a one-to-one perfect match, but it really is kind of creating a room that looks similar enough to the target. So this is the whole pipeline. It takes, I'm not going to go over too much details. I just want to point out that in this pipeline, we basically took like a model database. We try to retrieve furniture's objects from that database based on certain kind of loss numbers. And we apply, again, inverse rendering optimizations at the intermediate stages of this pipeline. Yeah, so yeah, I just want to say that the intermediate stages, we perform inverse rendering to automatically align furnitures, optimize camera poses, and also, of course, material and lighting, so that we can, in the end, get an output scene that's quite similar to the input image. Again, it's not a pixel-wise match, but nonetheless, it creates a fairly useful 3D model for the room. Because of that, because we can get a 3D scene for the room, we can basically move the camera and do post-editing, and as you can see on the right. Okay. Because, yeah, again, this scene is in basically standard, say, Blender format, so an artist can grab it and do post-editing on it relatively easily. Okay. Okay. So these are some of the inverse rendering pipelines I've shown. Next, I want to discuss a little bit about the speed of inverse rendering. Because as you have seen in a lot of discussions and so on, sometimes people worry that inverse rendering or any optimization for that matter can be very slow. As you have seen that it's still kind of a problem, but it's less of a problem already thanks partially to the development of systems, right? We now get faster and faster, say, differential renderers, optimizers, and everything. However, what I want to emphasize here is that there's actually a large research space for speeding up inverse rendering at an algorithm level, not just as like a better CUDA code level. So let me show you some examples. The first example is some of our recent work, is related to some of our recent work published at SIGGRAPH Asia, I think last year. The observation is like this. If we think about what happens during a inverse optimization, so here let me show an animation where we are optimizing basically a texture on an object, right? We show an animation, basically it's the state of the texture per iteration. If you think about it, if you connect all the state of the texture per iteration, it kind of looks like an animation, right? Because the state of we are gradually modifying the texture throughout the whole optimization, which I think is quite normal when you do gradient-based iterative optimizations, right? So it basically shows that, okay, we're essentially doing something like an animation. So can we make this process faster by adapting techniques people have developed in graphics for rendering animations? In fact, there are plenty of those. The underlying idea here really is that if you think about the animation, individual frames are not independent of each other, right? They're really close to each other with minimal changes. So rather than treating each frame as being independent, can we do something more smart so that we can speed up the whole process? Right, the answer is yes. And of course, there are multiple possibilities to do it. So in this work, we adapted a recent work, recent real-time rendering technique called Reaster. So it's a technique that makes smart reuse of samples across frames. So in this case, across iterations. Because of that, if you look at the what's shown on the bottom, on the right, we show a baseline rendering with very low sample count. Again, we're doing Monte Carlo here. With very low sample count, the baseline is way too noisy to work. However, at the same sample count, if we can reuse samples in a way similar to what people have been doing in real-time rendering, we can get drastically cleaner result at roughly equal time. Thanks to these changes, if we use that to optimize the texture, so here we are visualizing the optimized textures, the baseline kind of broke because of the high noise. However, at the same time, if we make better use of samples, we can achieve much better reconstruction, basically much faster inverse optimization by just reusing samples. Okay. So yeah, this of course is just one example for reusing samples across iterations in this case. And I want to emphasize that many additional possibilities are possible. Okay, so the last piece of work I want to mention is about batching. Again, this is nothing really new. So the fact is that when solving inverse problems with many, such as multi-view images, it's typically undesirable to render all of them per iteration. So the solution, which is quite common already, right, is to partially render the images. Right? By partially render the images, I mean you can either just render a few views, not all of the views, or for each view, you render some of the pixels, not all the pixels. Right? So this is essentially batching. Of course, the high-level question is how we decide which views or pixels to render, right? Normally, people just do it uniformly, right? People say, okay, if we have 100 views, maybe we just randomly pick 10. If we have so many pixels, maybe just randomly pick 10% of the pixels, and so on, right? However, we have demonstrated in a recent work that we'll show at that we will present at SIGGRAPH 2025, is you can do much better by not doing uniform sampling, but something else. But again, I'll omit exactly what the best probability is. So instead, I'm going to show you this example. So here, again, we have a synthetic example. Hopefully, it demonstrates the case, where we're optimizing the spatially varying color of these three objects. So you can see in the target, we have three objects. This is just a single view. We're observing these three objects by directly looking at them, and also their images in a mirror. That's why we can optimize both the front side and the back side of these objects with only one image, right? So again, we started with, this is the initial setting where the objects are textureless. There's no color variation, right? So it's a little hard to see here. We're doing this with a very aggressive level of batching, where we are rendering less than 5% of the pixels. That's which is shown in the middle. So that's why you can see the images are mostly black, because 95% of the pixels are not rendered. Okay. However, I think you can see some of the stuff being rendered there. Right? That's the images being pixels being rendered. So you can see that first things changes. You can see the optimization quickly focuses on the eyes of the textures. And a convergence is achieved quite quickly by only rendering less than 5% of the pixels. So you may wonder, okay, what happens if we don't do this fancy non-uniform sampling? What happens if we just do uniform sampling? Well, this is what happens. Still, we are rendering the same number of pixels. So if we just render it using uniform sampling, you can see, okay, some things are still being changed, but after the same number of iterations, the results are very far from convergence. So basically, in this work, we're trying to show that by doing pixel-level batching in a clever way, you can achieve drastically faster convergence. We also believe that this is an approach, and also here we're just showing optimizing surface color. It also applies to shapes and other type of optimizations. We even believe that it applies to like nerve type of optimization as well. Because again, when you do a nerve type of volume rendering, you don't have to render all the pixels either. So this is actually a quite general tool. So here I'm just giving two examples by showing that, by trying to say that inverse optimizations are not really scary anymore. And also there are a large space for further improving their performance beyond just having faster systems. Okay. So next, let me briefly discuss about the future problems and directions. So first, where are we right now regarding this physics-based differentiable and inverse rendering? On the differentiable rendering part, recently, again, although I haven't talked too much about it, significant progresses have been made. So there are some key takeaways or realizations. The first one is that physics-based rendering is now almost fully differentiable, although individual past contributions may be not because of visibility and so on. The second key realization is that discontinuities almost always exist, no matter how smooth your surfaces are. But fortunately, these can be handled. Okay. So on the inverse side, the first one is, as I just mentioned, the physics-based optimizations may be expensive, but it's less expensive thanks to the system development and can be made a lot faster if you know what you are doing and do things in a clever way. And also, as we demonstrated in the neural PPAR pipeline, it's very often beneficial to combine neural and physics-based pipelines to get the best quality possible. And of course, this is still a evolving field, just getting started, and many challenges remain. So what are the challenges? So let's go back to this analysis by synthesis picture again. So first, on the capture side, of course, we want clean target images, right? When creating a new capture system, it's not always easy. And we need a loss here. So of course, we want the loss to be discriminative, and we want robust priors because this is a well-known yield-conditioned, yield-post problem, as we run into ambiguities and sometimes local minima all the time. And of course, to run this type of optimization, we need a good initialization. So maybe neural methods are the way to go here. And finally, this is something I didn't discuss a lot, but is very important as well. If you need to optimize shapes, what is the underlying representation of your shapes, right? Do you use like a point cloud? Do you use a Gaussian mixture? Do you use an implicit surface, right? Do you use a mesh? Using different representations can profoundly change the behavior of your optimization. So what the best representation is, there's probably no single best option, but that's having a robust one is a good thing to look at. And finally, what I want to talk a tiny bit about is that there are more capabilities that we have developed in, say, differentiable rendering that hasn't really been kind of materialized when solving inverse problems yet. For example, now we know how to differentiate even more advanced light transport models, such as transient or time-gated light transport. So in this example, we are showing the renderings and their derivatives of some basic transient camera image. Right? These are images where only collect photons arriving at the sensor during a certain time window. So this apparently gives us more information and allows us to do this sort of non-line of sight imaging. So in this example, we're optimizing the shape of this object without looking at it. So you can see the camera is here, it's kind of behind the object, it's kind of blocked. But normally, if you don't have time-gated images, this is near impossible to do. But by only looking at a few time-gated images, we can actually infer the shape of this object, again, without even looking at it directly. But of course, this is still a very toy case, but we expect the kind of adopting this type of technology to solve even more challenging inverse problems, which can be considered like not possible even sometimes. For example, in non-line of sight configurations. Okay, so yeah, that's about it. Thank you for your attention. Also, of course, I'm going to thank my current and former students and collaborators and my funding agencies. And thank you.